So today's lesson is on integration by substitution. Okay, just to start this, we look at just the first part of this. We're looking at the common integrals, the ones that basically are from a formula sheet. We have a k involved there, which is our horizontal compression expansion, which affects our differentiation and integration. But these are ones that essentially, if they look like these, we just apply these rules. There's also the power rule. We can undo the power rule. But there's lots of integrals that don't fall under these categories. An example is one that I've given here, which is 2x over x squared plus 1. Well, the power rule does not apply here. We cannot isolate the power on a polynomial. It doesn't look like any of those integrals, standard integrals that we have. So we need some other strategies to do this. And one of the strategies that we can look at comes from the chain rule. It's basically undoing the chain rule. If you remember from the fundamental theorem of calculus that integration and differentiation are opposites. So integration and differentiation are opposites. Okay, one undoes the other. So if we look at the result of differentiating using the chain rule, we're going to end up with an expression that looks like this here. So the outside derivative times the inside derivative, which means then if we integrate some expression that looks like this, we can integrate it into the original embedded function, and that would be then our integral. So what we're looking for, what we can do is, this is what the notation looks like, and we can make the notation look slightly different, and we can just let the u be our g of x function. And if we do replacement for the g of x, the inside function, we get an expression, the notation kind of looks like this. And we can simplify this notation. If you look, the dx's will cancel out. And then we end up with an integral in terms of u, with the variable of integration being du. And since it's a consistent, we can just undo that derivative to get the original f of x, or in this case, f of u function. Okay, so this is the main idea of how it works. Well, where it comes from, but how do we make it work? Well, to make it work, we essentially are going to use the following criteria. We need to choose an inside u function where when we differentiate and generate a du, we're going to end up being able to accommodate the leftover pieces, or the outside piece here. Okay, so I'll give you an example here. So in this case here, the inside function is going to be the x squared plus 1 in the reciprocal function. So it's embedded inside the reciprocal function. And when we differentiate that inside function, du by dx, we end up with 2x. And if we do an algebraic rearrangement, move the dx over to the other side, we generate du equals 2x dx. So this is a key to doing this, in that we've now chosen an inside function, the x squared plus 1, where its derivative, when we rearrange it, du, accommodates the expression that is on the outside of that 1 over x function. So that's kind of the key. So when we do that and do the substitution, then replace the x squared plus 1 in the denominator with u, and notice that the 2x dx can now be replaced by the du. So we get this expression that looks like this. So we end up with 1 over u times du in the integral of that. Well, we now have a function in terms of u. We're integrating it with respect to u. Well, that's consistent. So we just need to integrate this like a regular integral. This is a standard integral. The integral of 1 over u ends up being log of u. And then since it's an indefinite integral, we include the plus c. So we've now integrated this expression. Now, we have integrated in terms of u, but we really kind of wanted x's in there. So what we're going to do then is, well, I want to change it back to x's. Well, in the green here, there I have my u in terms of x. So I'm going to replace that u with the x squared plus 1. So I get log of u plus c and the u now becomes x squared plus 1. There it is. There's the antiderivative of that original expression 2x over x squared plus 1. And we can check this, right? We can check this by, if we differentiate the integral, we should end up with what we started off with. So this is my check. If I differentiate, so d by dx of log x squared plus 1 plus c, the derivative is going to be 1 over x squared plus 1. There's my inside function, is now in the denominator, and I need to apply chain rule to the inside function times 2x plus the derivative of c is going to be 0, and there it is. If I simplify it, I end up with 2x over x squared plus 1. If I check my original integral here, yeah, that's my original function. Check, that works.